Hello students, in the last class we have dealt us something on the second important step which was employed in the field of metallurgy. Which was that? Yes, so we converted the concentrated ore into a crude metal which involved two steps. So the first one was that the concentrated ore was converted into its oxide, which was done by roasting and calcination. Then second one, we convert whatever that ore, oxide ore, was reduced by selecting a reducing agent. In order to select that particular reducing agent, we went through the thermodynamic principles of metallurgy and we have seen something on Aluminium diagrams, and lastly we had seen the applications of Aluminium diagrams, majorly included extraction of iron, extraction of zinc and extraction of copper. So today we shall see the next part in that case, that is electrochemical principles of metallurgy. Principles of electrochemistry can also be applied in the field of metallurgy. See, we have used all those thermodynamic principles to extract the metals, that is selection of reducing agent, isn't it? But there are certain elements or metals in general which can also be reduced by making the principles of electrolysis. Now in this case of electrolysis, what we generally take is we should take either the molten metal or it should be in the form of solution, both, any of the two, because we know current can be passed only in aqueous solution or in the case of molten metal. We cannot apply the principles of electrolysis to a solid state. We already know that. Okay. See, in order to isolate or select a reducing agent, we used one equation earlier which was delta G is equal to delta H minus T delta S, isn't it? So this was applicable for thermodynamics. Now in the case of this electrolysis, the slight modification is seen in the equation. Delta G is equal to minus NF E naught, where N is the number of electrons whatever that takes place during the process, and F Faraday, and E naught is the electrode potential. Whatever the redox couple we take here, that electrode potential of the redox couple will be your value of E naught. Looking into this equation, if the value of E naught, if this is positive, what we can say that generally the value of delta G will be negative and this process takes place, isn't it? We know if the value of delta G being negative, all the things are feasible and we can generally reduce that particular metal oxide as such. See, in generally most of the metals are highly reactive and hence they have a negative values for this electrode potential. So in that case they cannot be reduced by this technique, but there are certain elements which are low reactive, those can generally be separated from this principle of electrolysis. Okay, generally the one whichever is more basic will go into the solution and less basic ones are usually deposited on the surface of the metal. If you just see that generally in electrolysis deposition of the metal will take place at cathode. So at cathode, that is the negative terminal, the metal will deposit. Okay, this is regarding certain things on electrochemical principles of metallurgy. You have been given with an example of aluminium. Okay, we can extract aluminium from its molten bauxite, or you will take it as a molten alumina, and we end up with aluminium. So let us see into the extraction of aluminium, which is also called as Heroult process. Okay students, so the first one given here is extraction of aluminium. So the diagram of the electrolytic cell looks something like this, which I have already drawn for you, and we just will see what exactly happens in this procedure. Okay, so in order to apply electrolysis or the procedure of electrolysis, we need two major things. One, the electrolyte, and the other electrodes. So what are we taking as electrodes and what is the electrolyte used over here? So we shall see those things. See, first electrolyte. We have to pass current to a solution, isn't it? So we'll see what is the electrolyte used over here. See, the electrolyte used over here is, I have written here, molten Al2O3 along with Na3Al(F6). Na3Al(F6) is nothing but cryolite. Okay, molten alumina. This can also be told as molten alumina along with small amount of cryolite. Okay, so this will act as the electrolyte. Molten alumina is nothing but Al2O3 and cryolite with the formula Na3Al(F6). Now, what is the role of cryolite now? Why do we add this cryolite? You may be asked a question also like this, mention the role of cryolite in the extraction of aluminium. So the role of cryolite is to bring about conductivity. Role of Na3Al(F6). So there are two major roles. So one, it brings about conductivity. We have to conduct current, isn't it? So this will bring about conductivity. And next one, it will decrease the melting point of alumina. Whatever we take, that alumina or the chief electrolyte what we take, it should melt, isn't it? Because when passing current, it should be to the solutions only. So in that case, in order to decrease the melting point of alumina, we make use of small amount of cryolite. Students, it is not only cryolite, even you can add few amounts of CaF2. Calcium fluoride can also be added in order to bring about the conductivity or to decrease the melting point of alumina. Either you can add this cryolite or you can add this CaF2. Any two you can be add, and that we usually use one. Generally this cryolite is used. So this is our electrolyte. We take molten alumina along with cryolite. So the role of cryolite is to bring about the conductivity as well as it will decrease the melting point of alumina. Even you can also take this as a electrolyte itself. Okay, now we have selected the electrolyte. Next, what are the electrodes taken? See, we already know that in order to do electrolysis, we want two electrodes. So one is anode and the other cathode. See, I have written here, graphite is taken as anode, that is the positive terminal whichever is used in the principle of electrolysis, positively connected here. See, all those graphite rods are connected by means of a copper clamp, and that in turn is connected to the positive terminal. Okay, and we need a cathode, that is negative charged terminal we need. In that case, we take this steel vessel. So here that steel vessel which has a carbon lining, there should be a lining of carbon in that, and that is taken as cathode. So these are the two electrodes taken, graphite as anode and a steel tank or a steel vessel with carbon lining is taken as cathode. Now with these arrangements, what generally happens whenever you pass current? Whenever you switch on the key, okay, you might have seen those arrangements in your physics chapters. So in that case, whenever you switch on the key, what generally happens? See, there are two reactions which takes place here, major two reactions. So the one which will take place at anode, and it is written as reactions taking place at anode, and the one which takes place at cathode. Now we shall look into those two equations, what are reactions which generally takes place at anode and cathode. Okay, reactions taking place during electrolysis. Okay, so prior to write those reactions, so let me write, we have this Al2O3. Where is this? This is present as electrolyte which is present in the molten state. Now if you ionize this, what happens? We end up with Al3 plus and oxygen O2 minus. You know why this Al is 3 plus and why this has 2 minus, and you know to write the formula and all. We have already studied all these things in our practical sessions, isn't it? Now we'll write this as balanced. I have 2 Al here and I'll make it as 2 Al 3 plus, and I have oxygen, this is 3 O2 minus. Okay, we usually don't write this equation, but in order to understand the reactions which takes place, we want to know this equation. Okay, now we'll write what are the reactions taking place at cathode. See, I have already said that these metals being electropositive in nature, they are usually liberated at cathode. So I'll take that Al3 plus. Now my main intention is to get only this aluminium, so what I should do, I should make this as Al. Now I have this 3 plus and I have to make it 0, means what should I do? I have to add 3 electrons. So that will take up 3 electrons and will become as Al. So this is molten aluminium, and which will come out from here, that is near to cathode. You might observe the things. See, I have this steel vessel and that aluminium will come out near to that cathode only, not towards this anode. Anode is somewhere here. So our aluminium will come out here, that is aluminium 3 plus. Where was this Al3 plus, which was in the electrolyte or molten alumina, that will take up 3 electrons and will become Al, that is molten aluminium. Now you may ask where these electrons come from, isn't it? So for that we have another set of reactions, that is whichever the reactions taking place at anode. Now who is there at anode? At anode we have taken graphite. Graphite is nothing but just the carbon. So that carbon will react with the oxygen, or in general oxide, O2 minus, and will end up with CO. Now in order to balance this, I had 2 minus, and now this carbon has taken up only the oxygen. What else is left? I am left out with 2 electrons. 2 electrons, I will write it as E minus. You might see I have used only 1 O. How many O are there here? Still I am left out with 3 O2 minus. So once again one more reaction we can write. The same carbon will react with the remaining 2 O2 minus ions and will get converted into CO2, carbon dioxide gas, with the liberation. See, for 1 O2 minus we had 2 electrons. I have now 2 O2 minus ions are there, so which will release 4 electrons. Totally how many electrons? It is 6 electrons. If you just check out here, I have 2 aluminium ions, which 1 aluminium will require 3 electron. In that case, for 2 aluminium, how many electrons are needed? 6 electrons are needed, and we have that 6 electrons here. Okay, I hope you are clear with the things. Let me repeat, the reaction which takes place at cathode, that is mainly aluminium ion will take up the 3 electrons and will get converted as molten aluminium and will come out in this cathode. And at anode carbon is present, and that will react with the oxygen ions present here from that particular alumina, and it gets converted to carbon monoxide and carbon dioxide, liberating electrons. So these electrons will be taken up by aluminium ions to get converted into molten aluminium. Now if you write the overall reaction, that is the total reaction whichever is taking place here, what we write? Overall reaction. You may be asked a question also, write the overall reaction. In that case, overall reaction is very simple. So it is a reaction involving Al2 O3, which is our bauxite. This is going to react with carbon, that is anode. Here this is usually taken as the reducing agent. What am I going to get? My main intention is to get aluminium along with the liberation of carbon dioxide gas. So we have to write the balanced chemical equation, which I have already said. So let us balance this now. So here I have an odd O, or 3O is there, and here I have 2. So I will make it this as even, multiply the things by 2. So I have 2Al2O3. Now how many aluminium have been formed? 2 into 2, 4. So here I have 4Al. And how many? 2 3s are 6O. I'll make it as 3CO2. And here, in order to balance that, I have 3C. So 2Al2O3 plus 3C will give you 4Al plus 3CO2. So the equation is balanced. I repeat, we usually have to write the balanced chemical equations. Unbalanced chemical equations do not carry marks, so be very careful in balancing these equations. Okay, so this is regarding extraction of aluminium from alumina. This alumina, that is purified alumina, is obtained from leaching, which we have already discussed in our earlier classes. That alumina is taken as electrolyte along with the small amount of cryolite. So the role of cryolite, it decreases the melting point of the electrolyte, and on the other hand it also brings about the conductivity. Okay, carbon or graphite is taken as anode, and a steel vessel containing carbon lining is taken as cathode. During electrolysis, these are the reactions taking place inside that. So at cathode, aluminium is present, will take up the electrons and will come out as molten aluminium, and at anode, carbon will react with oxygen ions forming carbon dioxide and carbon monoxide. The overall reaction is something as such. See, this entire procedure, what I have explained, this is called as Hall-Heroult process. It is named as Hall-Heroult process. You may be also asked to explain Hall-Heroult process of extraction of aluminium, which is the same thing. You have to draw the diagram and you have to explain the things, or else you may also be asked to explain the extraction of aluminium from alumina or purified alumina, which goes something like this. See here, aluminium will be liberated at cathode, and who comes at anode? See, at anode, oxygen will come out at anode, O2. Oxygen gas will be liberated at anode, and molten aluminium will come out at cathode. This is something regarding extraction of aluminium by Hall-Heroult process. One example given in the electrolysis. Okay. Okay students, so one application was for aluminium, and next the second application given over here is extraction of copper. We have already seen copper by applying principles of thermodynamics, that is from copper 1 oxide, but here this copper is extracted from low grade copper. Low grade ore, or in generally we mention it as scrap. Whatever the things we don't know, whatever we don't require, what we do, we generally give to some people, right? So, and we'll get some money also. And from that, we make that extraction of copper can also be done from that low grade ore. So what generally they do here is, first one, they concentrate. The first step is to concentrate, isn't it? So the concentration is done by hydrometallurgy. After this concentration, it is then converted to its ore by leaching. So here they may use either an acid or bacteria to leach. So we exactly know what exactly is leaching. Okay, so that is leached by the action of acid or bacteria, and then it is reduced. So it can be reduced either by using iron, Fe, or hydrogen gas. So we'll just see. We are into the process of electrolysis, so I am interested in this third step. So what generally is, I'll take that copper in the form of copper 2 plus, copper ions are there. Either it can be reduced by taking Fe, iron can be taken. What happens? This Fe being more reactive will go into the solution and becomes Fe2 plus, and copper will deposit at the cathode plus Cu. Instead of using iron, you can also take hydrogen, so that is H2 or dihydrogen. So in this case also copper will come out as copper 2 plus will come out as copper, and hydrogen as H plus. So we have to balance. I have 2 hydrogen here and I have 2 H plus. So this is how we generally extract copper from low grade ores or scrap material, something as such. So it is generally concentrated by hydrometallurgy and then followed by leaching with the action of acid or bacteria, and finally it is reduced by taking iron or hydrogen, and the equations are something as such. So copper being a low reactive metal and will be deposited over the cathode. These are the two major applications whichever have been given in the electrochemical principles of metallurgy. So one was the extraction of aluminium, and another was the extraction of copper from low grade ores. Okay. Okay students, now we have seen the second step, that is reduction of the ore. Now you may ask, we have also studied oxidation. Why can't we use the principle of oxidation in order to extract the metal? Yes, we can use that, but the principles of oxidation, or we generally know what exactly is oxidation. Oxidation is nothing but addition of oxygen or removal of hydrogen. So oxidation is generally applicable for non-metals. We can't apply the principle of oxidation for metals. So one such example given to you here is the preparation of chlorine. Okay, oxidation reduction. This is usually, in that case, it is applicable. This oxidation is applicable for the extraction of non-metals. One example given to you is extraction of chlorine. See, this extraction of chlorine we have already studied in the last year. That is in your first year chemistry, somewhere in S block elements. In the preparation of sodium hydroxide, we made use of the same equation. You just try to recall what generally we did there is sodium hydroxide solution was taken and it was electrolyzed. So it was on electrolysis. What happened? Chlorine gas was liberated along with hydrogen. The same we write here also. Okay. So what we take in this case is we have that sodium chloride solution. We have Cl minus. I will write the ionic equation. So sodium chloride solution was taken with solution in the case plus H2O. So when subjected to electrolysis, the same carbon rod was taken as anode and mercury was taken as cathode, and they were subjected to electrolysis. We end up with an amalgam of mercury, and finally it was diluted with water to get sodium hydroxide. Okay, Kastner-Kellner cell was the method used for the isolation or preparation of particular sodium hydroxide, which we have already studied last year. The same equation I will make use of here. I have that chloride ions. From where do they come from? They come from sodium chloride, which is usually seen in sea water. This is treated with water and subjected to electrolysis. We end up with OH minus. In generally we end up with NaOH if you take NaCl, and along with the liberation of chlorine gas and hydrogen gas. So here chlorine will be liberated at cathode and hydrogen gas will be liberated at anode. See, if you calculate the value of delta G for this reaction, it will be around plus 422 kilojoules. Now if you convert that delta G into the EMF or electrode potential, we end up with the plus 2.2 volts. Now in our driving force should be there, we should overcome that, because I have already said positive ones are not this. So in that case, more over potential and other concepts are applied over here in order to make the reaction possible, so which you will study in details in a chapter on electrochemistry in your later classes. Okay, so in generally we end up with the chlorine here. If you just see chlorine here, it is -1, oxidation number is -1, so from -1 it is going to 0. So there is a increase in the oxidation number, indicates that this chlorine has undergone oxidation. This we have already studied in detail last year, isn't it? Okay, now one sentence given to you there is, now here I have taken aqueous sodium chloride. If you take a molten sodium chloride without any water, that is molten NaCl, and if this is subjected to electrolysis, then we don't end up with this NaOH, okay, remember, we end up with chlorine and molten sodium. Molten Na is obtained as the product of electrolysis, which you will study later in the chapter on electrochemistry. So this is one, that is in the extraction of non-metals. So there is one more example given to you here, applying the principle of oxidation and reduction, that is extraction of gold and silver, which we have already studied in leaching. So let us recall that once again. Okay. Okay, extraction of gold, silver. So the equations I have already written, it is just a recap, that's it. So what we do in the extraction of gold or silver, so for simplicity I write it as M, where M can be your gold Au or silver Ag. So this is dissolved in a cyanide solution. You can take potassium cyanide or sodium cyanide. Solution, I said, indicates plus water H2O in the presence of oxygen O2. Now what happens? When subjected to this cyanide, the metal gets dissolved in this particular cyanide and we'll end up with the complex. So I have MCN twice minus plus OH minus. Now I have told you to remember how to balance this equation also. So here we write it as 4 and we multiply that 4 by 2, which is 8, and we divide this 4 by 2, which is 2. 4, 8, 2, and finally here I have 4m, and here also it is 4m Cn2 twice minus, and here also it is 4 OH minus. Now if you just see here, if I have taken Au here, I will be ending with Au. So generally what has happened here is that particular metal with an oxidation number of 0 have went into an oxidation state of plus 1 in this complex. So there is an increase in the oxidation number, indicating that oxidation of this particular metal has taken place here. Okay, so that is, if you take Au, Au will go to Au plus, and if you take Ag will go to Ag plus. So I have written commonly as M. In the next step, what we do? We take this, isn't it? If you just recall, we take that the same complex of gold and finally we displace it by taking or by reacting with zinc. So zinc will replace this particular metal and I have Zn Cn 4 times 2 minus plus M. So here I have 4 Cn, in that case to balance I will take it as 2 M Cn 2 and here I will make it as 2M. If you just check here what exactly has happened here, your metal was in the +1 oxidation state here, which I have already mentioned, and that is being converted to this one, that is M0. Oxidation number is 0. So here from +1 to 0, what has happened? There is a decrease in the oxidation number and this has undergone reduction, wherein which we use zinc as a reducing agent. Okay, so this is another example for the concept on oxidation and reduction, which is nothing but extraction of gold and silver, wherein which we dissolve that particular metal in a cyanide solution. In the presence of oxygen, we end up with the complex of that particular metal, and that finally it is reduced by treating with zinc and we end up with this impure metal. So these are two examples which have been given in terms of oxidation and reduction. One was the extraction of chlorine and another the extraction of gold and silver. So with this, the second method employed in the process of metallurgy is completely over, and in all these steps we have ended with the impure metal and finally we are left out with the purification of the metal that we will see in the later session.